Spider Derivative Man, back talking to you about the product and quotient rules. Another question, what is the Hulk's favorite video game? Super Smash Brothers!
First thing we're going to talk about is the product rule. It says the product of two differentiable functions f and g is itself differentiable. Moreover, the derivative of f times g is the derivative of the first function times the second function plus the first function times the derivative of the second function. So that's what this is saying down here. We have two differentiable functions f and g being multiplied together. And I want to take the derivative of that product. What I do is I use the product rule, which says I take the derivative of the first function times the second function plus the first function times the derivative of the second function. So again, product rule is derivative of the first times the second plus first times the derivative of the second. The quotient rule says the quotient of two differentiable functions f and g is itself differentiable at all values of x for which g of x is not equal to 0, because you can't have the denominator equal 0. Moreover, the derivative of f divided by g is given by the derivative of the numerator times denominator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So here we have a quotient, f of x divided by g of x, and both of these functions are differentiable functions. If I want to take the derivative of this quotient, f of x over g of x, what I'm going to do is I'm going to take the derivative of the numerator times the denominator minus numerator times derivative of denominator, all over the denominator squared. Notice that the top kind of looks like the product rule, except we have a minus here. So again, the quotient rule says if you have two differentiable functions and you want to take the derivative of the quotient of those two functions be divided by each other, all you have to do is take the derivative of the numerator, multiply it by the denominator, then subtract the numerator times the derivative of the denominator, then put that all over the denominator squared.
Venom creeps me out! It's example time!
Now example 1 says find the derivative of the following functions. We have h of x is equal to x times e to the x. So we want the derivative of this function. Notice that it's a function times a function. Because we're taking the derivative of a function times a function, we need to use the product rule. And what does the product rule say? Well, it says when we have the derivative of a function times a function, we take the derivative of the first function, so it's going to be the derivative of x, and then multiply it by the second function, e to the x, and then we add the first function, x, and then multiply it by the derivative of the second function, e to the x. So derivative of the first times the second plus first times derivative of the second. So now all we have to do is take the derivatives and then simplify. So here, derivative of x is just going to give you 1, and the derivative of e to the x, that's the easiest derivative, it's just e to the x. 1 times e to the x gives you e to the x, and then x times e to the x is x e to the x. Now you could leave your answer like this, or you could see that both of these terms have an e to the x that I can factor out, and I can write my answer like this, and I'm done.
My spidey sense is tingling. Must be time for a U-try.
We are again taking the derivative of each of these functions. Here we have a function with two terms. So when we take the derivative of this function, we have to take the derivative of each term. Now we're ready to take the derivative. So let's first take the derivative of this guy here. Oh wait, I have this number multiplied to my function. Anytime you have a number, a constant like this, multiplied to your function, you can actually take that number and move it out front and then multiply it on at the end. You don't have to worry about that till the end of the problem. But you could keep it in here if you wanted to. It just makes your derivative process a little bit more complicated. So what I would do is for each of these functions, since we have a constant in here, I would take that out and then multiply it on at the end. It makes taking the derivative of each of these functions much easier. Now, let's look at this first function right here. We see that we have x times cosine of x. Now, x and cosine of x, those are two separate functions. So when I take the derivative of this, I need to use the product rule. And the product rule says take the derivative of the first times the second plus the first times the derivative of the second. That's what we have here. Note that this is the same still. We haven't taken the derivative of that yet, and we left the 2 out front. We're going to distribute that at the end. So now let's take the derivative of each of these things we're taking the derivative of. Derivative of x is just going to be 1. The derivative of cosine of x is negative sine of x, and the derivative of sine of x is cosine of x. Now let's simplify. 1 times cosine of x is cosine of x. X times negative sine of x is negative x sine x. And then over here, negative 2 times cosine of x is just negative 2 cosine of x. We also have to distribute that 2 to each of these terms, and now we have this. Is there anything else we could simplify? Yeah, 2 cosine of x minus 2 cosine of x, those cancel each other out, and we get our derivative is negative 2x sine of x. Over here, doing the same thing, taking the derivative. Now, whenever you have a radical and you're taking the derivative, you want to change that into a rational exponent. So here, the square root of s is the same as s to the 1/2 power. Now, we have two functions being multiplied together, and when we take the derivative of two functions being multiplied together, we need to use the product rule. And the product rule says we take the derivative of the first function, multiply it to the second function. Then add that to the first function times the derivative of the second function. Now let's take the derivative here. Derivative of s to the 1/2 power. I'm going to use the power rule. So this 1/2 comes out front, then it becomes s to the 1/2 minus 1 power, which is going to be s to the negative 1/2 power. Over here, when I take the derivative of s squared plus 8, I take the derivative of each term. The derivative of s squared becomes 2s to the first, and derivative of 8, that's just constant, so that becomes 0. I then add these two together. 2s plus 0 is just 2s. Now I have to simplify further. So 1/2 s to the negative 1/2. I have to distribute that to the s squared and to the 8. So let's first multiply these two together. S to the negative 1/2 times s to the second. They are like bases, so I add the exponents together. That means I get 1/2 s to the 3/2 power. Then I multiply this to the 8. I multiply the 1/2 and the 8, I get 4. So I get 4s to the negative 1/2 power. Lastly, I multiply these two together. It's going to be 2s to the 1/2 times s to the first. They're like bases, so I add the exponents. 1/2 plus 1 gives me 3/2. Now, can we simplify this? Yeah, we have two like terms. We have s to the 3/2 here and s to the 3/2 here. So we're going to add together the coefficients. 2 plus 1/2 is going to give me 5/2. And then this over here, s to the negative 1/2 power. I don't want a negative exponent in my answer, so I bring this down to the denominator. Now I want to combine these. So how do I do that? I need to make this one fraction. So I take this s to the 3/2 and move it up in the numerator with the 5, which is something I can do. I then see that in order to add these together, they have to have a common denominator. So this fraction I'm going to multiply by 2 over 2, and this fraction I'm going to multiply by s to the 1/2 over s to the 1/2. Now how does that work? What's s to the 3/2 times s to the 1/2? Well, again, you add the exponents, you get s to the second power because it's 4 over 2. Now they have a common denominator, so I can add these numerators together. I get 5s squared plus 8 all over 2s to the 1/2 power. Or if I want to rewrite this as a radical, 2 rad s. Again, you could rationalize this where you multiply the numerator and denominator by rad s, but I'm just going to leave it like this with the radical and denominator. That's fine in this class. Example 2 says find the derivative of the following functions. Here we have f of x is equal to 5x minus 2 over x squared plus 1. Note, we have a function being divided by another function. Because we're taking the derivative of a function being divided by another function, or the quotient of two functions, what we're going to do is we're going to use the quotient rule. The quotient rule says we take the derivative of the numerator, multiply it to the denominator, then subtract the numerator times the derivative of the denominator, all over the denominator squared. So now let's simplify this. Derivative of 5x minus 2, we take the derivative of each term, so the derivative of 5x is just going to be 5 times 1, and derivative of 2 is going to be 0. Over here, the derivative of x squared is going to be 2x, and then derivative of 1 is going to be 0. We then simplify. 5 times 1 plus 0 is just going to be 5, and then 2x plus 0 is going to be 2x. Can I simplify this further? Yeah, I can distribute the 5 to the x squared and to the 1. Over here, I can distribute the 2x to the negative 2 and to the 5x. Now I can distribute this negative sign to the 10x squared and to the negative 4x. And can I simplify anything else? Yeah, I have two like terms here. We have 5x squared minus 10x squared. That's going to give you negative 5x squared. And then plus 4x plus 5. Nothing else simplifies. We are done.
Don't be a vulture. Do your own work. You try.
Okay, so we're again taking the derivative of this function. Note that when we're taking the derivative of a function that has a radical in it, we always switch that to a rational exponent because we can't take the derivative of a radical, but we can use the power rule if it's x to the 1/2 power. Now we're taking the derivative of this function divided by this function, this rational function, this quotient. So to take the derivative of this quotient, we need the quotient rule, which says we take the derivative of the numerator, multiply it to the denominator, subtract the numerator times the derivative of the denominator, and put that all over the denominator squared. Now let's go ahead and take some derivatives. So here, derivative of x squared, we use the power rule, it'll be 2x to the first. Over here, take the derivative of 2x to the 1/2 plus 1, we got to take the derivative of each term. So the derivative of 2x to the 1/2, 2 is just a constant, so by the constant multiple rule, that gets to stay out front, and we multiply that on at the end. So x to the 1/2 power, when we take the derivative of that, becomes 1/2 x to the negative 1/2 power, and derivative of 1 just becomes 0 because that's a constant. Now let's simplify this over here. 2 times 1/2, those just cancel each other out. We just get x to the negative 1/2 power. Plus 0 is just x to the negative 1/2 power. Perfect. Now let's distribute this 2x here to the 2x to the 1/2 and to the 1. So 2x times 2x to the 1/2. 2 times 2 gives you 4. X to the first times x to the 1/2. We add the exponents together because they're like bases, and we get x to the 3/2 power. 2x times 1 just gives you 2x. Over here, x squared times x to the negative 1/2 power. Again, multiplying like bases, you add the exponents. So 2 plus negative 1/2 just gives you 3/2. Now, can we combine anything? Yeah, these are like terms. They have the same variable with the same degree. So 4x to the 3/2 minus x to the 3/2 gives you 3x to the 3/2. Now, I'd be okay if you left your answer like this, but if you want to simplify it a little bit further, each term in the numerator has an x that you can factor out, and if you factor out an x from x to the 3/2 power, you just subtract 1 from that, you get x to the 1/2 power. So it looks something like this: x times the quantity, 3x to the 1/2 plus 2. The last thing, if you want to get rid of this rational exponent here and this rational exponent here, you could just make those radicals and you're done. Now, example 3 says find f prime of x and f prime of c. So here we have a function and we have a c value. First thing we're going to do is find the derivative of our function f. Now, note that we have a function being divided by another function. We have a rational function. Since we want to find the derivative of this quotient, we have to use the quotient rule, which says we take the derivative of the numerator, multiply it to the denominator, then subtract the numerator times the derivative of the denominator all over the denominator squared. Now, let's take the derivative. So derivative of x minus 4, we take the derivative of each term. Derivative of x is 1, derivative of 4 is 0. Over here, derivative of x is 1, derivative of 4 is 0. Now, 1 minus 0 is 1. 1 plus 0 is 1. 1 times x plus 4 is x plus 4. 1 times x minus 4 is x minus 4. We then distribute that negative to the x and to the negative 4. It becomes minus x plus 4. So the x's end up canceling each other out. The 4's add together to give you 8. And we have our first derivative, f prime of x. But we also want to find f prime of c, which means we're going to take our derivative that we found. And we're going to take our c value, which is 3, and plug it in for x here and here. We then simplify. 3 plus 4 gives you 7. 7 squared gives you 49. So we have found f prime of c, or in this case, f prime of 3, which is 8 over 49. This is the derivative of our function f at x is equal to 3. This is the slope of our tangent line to the curve at x is equal to 3. It's the instantaneous rate of change of our function at x is equal to 3. Now, example 4 says find the derivative of the function without using the quotient rule. So you're going to run into a lot of functions that look like these that seem to require the quotient rule, but actually don't, and are much easier if you don't use the quotient rule. So technically on both of these, you could use the quotient rule, but it's super hard and it's not necessary. Here, because we have a constant in the denominator, and that's it, there's no x, there's no variable in the denominator. What we can do instead of using the quotient rule is rewrite this as 1/6 times the quantity x squared plus 3x. Now what I can do is take the derivative of this, and when I take the derivative, I just have a constant being multiplied to my function. So I use the constant multiple rule and take this 1/6 and just move it out front and multiply it on at the end. So now over here, I'm going to take the derivative of each term separately. Derivative of x squared becomes 2x to the first, and the derivative of 3x, I just take the derivative of x and then multiply 3 on by the constant multiple rule, and I get 3 times 1. Now, if I were to simplify this, I could either distribute the 1/6 to the 2x and to the 3, and I get 1/3 x plus 1/2, or I could just rewrite it as 2x plus 3 all over 6. Either way, this is my derivative. And I got it without using the quotient rule. You could use the quotient rule, but it takes way longer and is much harder. Part B, doing the same thing. I am taking the derivative of a rational function, but this time, again, I don't have a variable in the numerator. I just have a constant. Because of that, I can rewrite this so I don't have to use the quotient rule. I'm going to rewrite this function as 9/5 times 1 over x squared. Or instead of 1 over x squared, better yet, I can use x to the negative 2nd power. The reason I do that is because when I take the derivative, I can use the constant multiple rule, take the 9/5, move it out front, and then I can take the derivative of x to the negative 2nd power just by using the power rule, right? I take that negative 2, move it out front, and then subtract 1 from my exponent, so I get negative 2x to the negative 3rd power. Now, to simplify this, I take that x to the negative 3rd, move it back to the denominator, then multiplying fractions, I just multiply the numerators together and denominators together, and I have my derivative, and it was much easier than using the quotient rule.
You try.
Okay, so again, both of these functions look like they require the quotient rule. This one over here even has variables in the numerator and denominator. But if I do some simplifying, I can actually cancel out maybe that variable in the denominator. So here, if I were to distribute that -3 to the 3x and to the -2x squared, I end up getting this. And you see that both terms in the numerator have an x that I can factor out. And then that x does cancel out with the x in the denominator. So now I don't have a variable in the denominator, which means I can rewrite this as 1/7 times the quantity, -9 plus 6x. Now when I take the derivative of this, I see that I don't require the quotient rule. All I have to do is just take that 1/7, move it out front by the constant multiple rule, take the derivative of each term here. Derivative of -9 is just 0. Derivative of 6x is just 6 times 1, because I just take the derivative of x, which is just 1, and then multiply it by 6 by the constant multiple rule. Here, 0 plus 6 times 1 is just 6, and then 6 times 1/7 is 6/7. That's my derivative. Here, same thing, except my denominator already doesn't have a variable, which means I can just rewrite this right away as 5/8 times x to the 4th. Now when I take the derivative here, I can then use the constant multiple rule and just take that 5/8, move it out front and multiply it out the end. I then take the derivative of x to the 4th using the power rule, and I get 4x to the 3rd power. I then can simplify this, 4x to the 3rd times 5/8. The 4 and the 8, actually the 4 cancels out and the 8 just becomes a 2 down here, so I get 5/2 times x cubed, or you could write it as 5x cubed over 2, either way. Now example 5 says find the second derivative of the following function. So here we want to find the second derivative of this function. So to find the second derivative, you find the first derivative and then find the derivative of that. So let's find the first derivative first. So to find the derivative of this function, it's got multiple terms, so we find the derivative of each term separately. The derivative of x squared is just going to be 2x to the first. Derivative of 6x, we just take the derivative of x, which is 1, and then multiply on the 6 by the constant multiple rule. And derivative of -5 is just -0. We then simplify this. This becomes 2x plus 6, and that is our first derivative. But to find the second derivative, we then have to take the derivative of our derivative. So to take the derivative here, we just take derivative of each term in our first derivative. So the derivative of 2x is just 2 times 1, and derivative of 6 is just 0. So we end up getting 2 times 1 plus 0, which is just 2. So the second derivative of this function up here is equal to 2. Part B, doing the same thing. We want to find the second derivative. This one's a little more complicated. So here we have a rational function, a function divided by another function, and there's no real way to simplify this or take out a constant, so I am going to have to use the quotient rule here. So I take the derivative of the numerator times denominator minus numerator times derivative of denominator all over denominator squared. Derivative of x is just going to be 1. Derivative of x plus 1 is going to be 1 plus 0. I then simplify this. 1 times x plus 1 is x plus 1. X times 1 plus 0 is just x. I can then subtract the x and the x. Those cancel each other out. I just get 1 over x plus 1 squared. So this is my first derivative. But I want the second derivative. So I again have to take the derivative here. Now the only issue is I again have a rational function. I have something over something, except here in our numerator, it's just a constant. So if I were to take the derivative of this, there has to be a way to do this without using the quotient rule. And there is actually. If I were to rewrite this as x plus 1 to the -2nd power, I could then use the chain rule to take the derivative of this. The only catch is you haven't learned the chain rule yet, so you have to do the quotient rule, which says the derivative of the numerator times denominator minus numerator times derivative of denominator all over denominator squared. So here, derivative of 1 is just going to be 0. Over here, derivative of x plus 1, the quantity squared, that requires the chain rule, but you don't know how to do that yet. So what we're going to do is we're going to simplify this by doing x plus 1, the quantity, times x plus 1, the quantity, by foiling that, and we end up getting x squared plus 2x plus 1. Now we can just take the derivative of each term separately. So this becomes 2x to the first plus 2 times 1 plus 0 when we take the derivative there. Here, 0 times this just makes that whole thing 0. Now this over here just simplifies to 2x plus 2, but it's 0 minus 2x plus 2. So we have to distribute that negative to the 2x and to the 2, so it becomes negative 2x minus 2. Now each of these terms in the numerator has a negative 2 that we can factor out. And why do we do that? Because this x plus 1 to the first, we can cancel out one of the x plus 1s in the denominator. So it becomes negative 2 over x plus 1 to the 3rd power. And you're done. Spider-Man, Spider-Man. You Okay, doing the same thing. So we're finding the second derivative, which means we're going to take the derivative of this and then take the derivative of that derivative. So how do we take the derivative of this? Well, again, we have a constant being multiplied out front of our function. So we're going to take that 6, move it out front, and just multiply it on at the end using the constant multiple rule. Now all we have to do is just take the derivative of x to the 3/4. So we use the power rule. It becomes 3/4 x to the, what's 3/4 minus 1? That'd be negative 1/4. Now I can simplify this. 6 times 3/4. 6 is the same as 6 over 1, so it becomes 18 over 4. And I could simplify this and divide each of those by 2. I get 9 over 2 times x to the negative 1/4. Or, if you want to put that back in the denominator, you could. But we're going to have to take the derivative of this again, so I just leave it like this. Now, let's take the derivative of our derivative to get the second derivative. So to take the derivative here, it looks like we would need the quotient rule. But, as you can see, there is no variable in the numerator. So what we can do then is instead rewrite this as 9/2 times x to the negative 1/4 power. With this, we can take that 9/2, move it out front of the derivative sign using the constant multiple rule, and now all we have to do is just take the derivative of x to the negative 1/4 and then multiply it to 9/2. So we don't need the quotient rule. So what's the derivative of x to the negative 1/4 power? Well, we use the power rule. It becomes negative 1/4 x to the negative 1/4 minus 1 power, which is negative 5/4. Now to simplify this, we multiply these two fractions together. We get 9 over 8, and it's negative. So we get negative 9 over 8 times x to the negative 5/4. Or if you want to take that, put it in the denominator, make it a positive exponent, you could. Here, let's take the derivative of this function and then take the derivative of that to get our second derivative. So derivative of cosine of x, we know is negative sine of x. Now to get the derivative of negative sine of x, note that this negative right here is the same as negative 1 times sine of x. So we need to use the constant multiple rule. So I'm going to take that negative 1 and move it out front. Then I take the derivative of sine x, which is just cosine x, and then multiply it to the negative 1, and I get negative cosine of x. That's my second derivative of cosine of x. Now, example 6 says, use the graphs of f and g. Let p of x equal f of x times g of x and q of x equal f of x divided by g of x. So we want to first find p prime of 0. So what we need to do in order to evaluate this is find the derivative of our p function and then plug in 0 for x. So let's first find the derivative of our p function. P of x is equal to f of x times g of x. So if we want to find the derivative of that, we need to use the product rule because we have a function times a function. The derivative of the first times the second plus the first times the derivative of the second. Now what we can do is we can take the derivative of f of x. Derivative of f of x is just f prime of x. The derivative of g of x is just g prime of x. So we have successfully taken the derivative of our p function. Now we need to evaluate p prime of 0. Well, how the heck does this work? Well, look at our graph over here. F prime of 0. If I want to evaluate that, I just look at x is equal to 0. And what is the slope of my function f at x is equal to 0? Well, it looks like we're going up 2, right, 1. So that would be up 2 over 1. That's a slope of 2, which means the derivative of my function f at x is equal to 0 is 2. So I'm going to plug in 2 for f prime of 0. What is g of 0? Well, g of 0 is just whatever the y value of the function g is at x is equal to 0. And that would also be 2. Look at that. So it's going to be 2 times 2. Plus f of 0. What is the y value of the f function at x is equal to 0? That would be 1. And then g prime of 0. What is the slope of my g function at x is equal to 0? Well, we're going down 1, right 1, down 1, right 1. So that is a slope of negative 1. That's how you evaluate this. Now all we have to do is just simplify. 2 times 2 is 4. 1 times negative 1 is negative 1. 4 minus 1 gives you 3. And that is what p prime of 0 is.
Your turn.
Okay, doing the same thing here, except this time we're finding q prime of 4. Now, q of x is equal to f of x divided by g of x. So if we want to find the derivative of q at x equals 4, we need to first find the derivative of the q function. And because it's equal to f of x over g of x, when we take the derivative of that, we need to use the quotient rule. And the quotient rule says if we take the derivative of a function divided by a function, it's going to be equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all over the denominator squared. So now we have successfully taken the derivative of our function q. We now need to evaluate q prime of 4, which means we're going to take 4 and plug it in for each of the x's. Now we're going to take each of these piece by piece and figure out what they each equal. So f prime of 4. F prime of 4 means the slope of my function f at x is equal to 4. So at x equals 4, the slope of my function f, oh, that's a horizontal line. So that's a slope of 0. So I'm going to plug in 0 here for f prime of 4. G of 4 means the y value of my g function at x is equal to 4. So what is the y value of my g function at x equals 4? That is 1. So we put a 1 here. Minus f of 4. F of 4 means the y value of my f function at x is equal to 4. So at x is equal to 4, the y value of my f function is negative 1. So I plug in negative 1 here. G prime of 4. G prime of 4 is the slope of my g function at x equals 4. So we go over to x equals 4. The slope of my g function, we're going up 1, right 1, up 1, right 1. That is a slope of 1. So I plug in 1 here. G of 4 we already found was 1, so we plug that in. And now all we have to do is simplify. 0 times 1 is 0. Negative 1 times 1 is positive 1. So 0 plus 1 over 1 is 1. And you're done. Now example 8 says match the following position function graphs to their corresponding velocity and acceleration functions. So we've done this before, except this time now we have position, velocity, and acceleration. We have all three of these functions. So let's start with our position function. Starting with A, we want to match it with its corresponding velocity function. Now remember, the slopes of the tangent lines to the curve of my position function, my original function, correspond to the y values of the graph of the derivative, or in this case, the graph of velocity. So let's look at graph A. The slopes of the tangent line to the curve are positive, and as time increases, these slopes get more and more and more positive. So we are looking for y values in the graph of our velocity that start off positive and get more and more and more positive. Well, that would have to be D here. We have y values that start off positive and get more and more and more positive as time increases. Now let's figure out which acceleration graph matches with this velocity graph. Again, acceleration is the derivative of velocity. So that means that this graph, if we're looking at the slope of this graph, it's just a constant positive slope. So that would match with a constant positive y value down here in the graph of acceleration. So which of these has a constant positive y value? Well, if this is our t-axis, then this would be a constant positive number. So D would match with B. There we go. We got all three. Now let's go with B. If B is our position function, we are looking for y values down here that match the slopes of the tangent lines to the curve, because velocity is the derivative of position. So the slopes of the tangent lines to this curve start off very positive and then get less and less and less positive as time increases and approach 0. So which y values here start off positive and then approach 0 as time increases? That would be this one right here, graph of C. Then we do the same thing. Acceleration is the derivative of velocity. So which of these graphs down here have y values that match the slope of this graph? Well, this is a constant negative slope, so we're looking for a y value that is a constant negative number. So that would be this one, and that would be this one. So let's look up here. This has a constant negative slope, and so does this one. Well, this slope is more negative than this slope. So we know that this must be the more negative y value, which means this graph should match with this one as its derivative. Now let's go to C. C is a graph that starts off with slopes of its tangent lines that are very positive and then get less and less and less positive, and then right around the middle of our t-axis we get a slope of 0, and then these slopes get more and more and more negative as time increases. So we're looking at the velocity function, the derivative of the position function, and we're looking for y values that start off positive and then approach 0 towards the middle and then get more and more and more negative as time increases. So C would have to match with A right here. We again saw that the graph of C right here had a constant negative slope that wasn't as steep as this one, which is why the derivative of this graph would be this one right here. Since this one over here, the y value is less than this one over here, we can see that D would have to match with A right here. Lastly, the graph of D is our position function. It is a constant positive slope followed by a constant negative slope. We got a corner. So in our velocity function, we need a y value that is a constant positive number followed by a y value that is a constant negative number. That's why D matches with B right here. And then the derivative of our velocity function would be our acceleration function. So we're looking for a 0 slope followed by a 0 slope. So 0 slope, 0 slope, that would be C right here. So that's how those work.